ahead, Will. Where do you have to go?
Miss Julie, you have to catch my bus.
Will said he has to catch his bus soon. I said, are you going to play it in the orchestra when you catch it? Okay, that's our joke of the day. Anyway, a system is consistent if at least. So we're dealing with systems of equations, and that's what this whole chapter is all about. Solving systems of equations, at least this first part. And you guys have solved systems of equations using several methods. There's substitution, remember that? Substitution, elimination. You can solve them by graphing. And solving a system means finding what x and y equals, right? But sometimes systems don't have solutions. So it says a system is that should say is. A system is consistent if at least one solution exists. A system is inconsistent if no solution exists. If lines or planes in 3 dimensions are parallel, then there's no solution. Okay, right? If you were to have 2 lines that that's a line and that's a line, they never cross, then those lines wouldn't have a solution, right? But if they do cross, then the solution to that equation is right there, okay? And if lines are the same line in disguise, so sometimes you'll see something like, I don't know, x plus 2y equals 6. And then they'll give you another equation. Y equals negative 1/2 x plus 3. And they'll say, solve the system. Solve the system. You know what's true about this line and this line? They're exactly the same line in disguise, right? Because if I subtracted x from this side and then divided by 2, I would end up getting this, okay? And that means those are the same line, in which case there are infinitely many solutions, meaning every x and y value that you plug into that system will work, okay? So 2-dimensional example. So here's an example of a problem which is one of those things. So to solve this, do you remember the elimination method? What would I do to solve this system? Add the 2 equations together. When you add the 2 equations together, I get, look what happens. I get 0 equals 0. If you get something like 0 equals 0, or 5 equals 5, or something like that, or 6 equals 6, that means the system is consistent and there are infinite solutions, okay? Because these are the same line in disguise. I think if I multiply this equation by -1, I would get this equation, right? Okay, so infinite solutions, same line. Okay? Now, and if you got something like 3 equals 7 or something weird like that, or 0 equals 8 or something like that, that means those lines are parallel and there's no solution. So if you're solving by elimination or by substitution or any of those methods and you end up with something like this, that means that there is no solution, okay? But if you find an x value and a y value, then there is a solution. Oh, I forgot to do my favorite problem that I made up. So let's go back and look at that favorite problem, because here's a problem that actually has a solution. At the CU Event Center, look, I made this one. You can buy basketball tickets for $10 or $11. Couldn't you do that? Those of you who went. Didn't know that. I don't know why anyone. I think it was $11. Was it $11? It was kind of weird for the reserved seats. I didn't even know there were reserved. Were there reserved seats? I don't know. When I went to.
It was like the ones with the bucket seats.
Oh, really?
Yeah.
I just sat wherever. But that's on tape. I could get arrested. Okay. Anyway, I only paid 10. If 4,000 tickets were sold at the girls' state basketball game and they took in $41,000, how many of each ticket were sold? So this is a case in which you have to set up some stuff to solve the problem. So you to set up a system. So you have to let x equal, I don't know, number of $10 tickets, a number tickets, $10 tickets sold, and let y equal the number of $11 tickets, and then you can set up the system of equations, and this is a pretty easy one. You can say that x plus y has to equal how much? 4,000. Right? And you have done this before, right? In Algebra 1 or Algebra 2. But then, what people always forget is you have to have another equation, 10x plus 11y equals 41,000. Good? And then I have to solve that system. How would I solve that system? Two different ways. You could do substitution, solve for y, right? And then plug it in. I think I'd rather do elimination in this one. So if I want to do elimination, what I would do, first I'm going to take a picture of this and move it so I have more room. Okay? So here's my equation. What could I multiply this top equation by? To get rid of one of the variables. Yeah, multiply by either 11 or negative 10. So I'm going to multiply this top one by negative 10. Okay? And when I multiply everything by negative 10, that equation becomes negative 10x minus 11y equals negative 40,000. Is that right? What? Oh, because I'm not there. Sorry. Thank you. Negative 10 1. Thanks, Fred. Okay? And then I draw a line under there, and I add my two equations. Okay? And then I get y equals 1,000. Right? And so x would have to be equal to, right, 3,000. You take that number and plug it back into either of your two, and this is the easier one, right? So if I plug 1,000 in here, I get x equals 3,000. Very simple problem. Follow that? Okay. You've done that kind of stuff before, right? Yeah? Okay. So, going back, two-dimensional examples, we did that. Three-dimensional system. So with three-dimensional systems, I just talked to Mr. Beamer to make sure I was right. But if you graph any one of these and you have like a three-dimensional coordinate system, you end up with a plane, okay? And planes can intersect in a variety of ways. And I looked on the internet and I found 3 different ways there's even more than this ways that they could intersect. But you could have 3 parallel planes, in which case you would have no solution, right? You could have planes intersecting at one line, in which case if I solve this system and I end up with something like, just for instance, if I end up with something like x plus y plus z equals 7, okay? That's another equation of a, no, that would be a line. If I end up with something like x plus y equals 7, I'm not sure. But you can end up with just a line as your solution, in which case you would have infinite solutions, okay? Or you could end up with these planes intersecting in 3 lines. That's kind of hard to see on both of these. But see how they can intersect in 3 places like that? And that would be no solution. Okay? And the only way you're going to get one solution, which is not that common, is if 3 planes intersect at one exact point. And that would look like that. So in order for you to get it like an x, a y, and a z, then these 3 things have to intersect at exactly one point. And the only way for that to happen if they're all on like different, going in different ways. Okay, so they can't be parallel to each other or anything like that. So let's look at this one. 3-dimensional examples. I'm just going to kind of take you through this a little bit. I'm not going to do the whole thing because I'm not going to make you solve 3-dimensional systems by hand because it's kind of a pain in the neck. Have you done that before? You have to do like a double elimination. So let's see what happens with this one. What you need to do is take two equations and try to eliminate a variable, and then they take two of the other equations and try to eliminate one of the variables, and then you take those two resolved equations and you eliminate a variable from those. Yes, sir?
Can you just use a matrix?
Yeah, that's what I'm going to teach you in a minute, but I just want to show you. But yeah, we're going to do matrices in a minute. Okay? So if I have this thing right here that I'm trying to solve, so here it is. What I would do is try to eliminate a variable between these first two equations. So if I combine these two, I think you guys are smart enough that we could just add these two together. If I add these two together, what do I get? What's x and negative 2x? Negative x. And if I add 2y and y, what do I get? Plus y. And if I add negative b and c together, what do I get? Hello? 0. So that disappears, and I get 9 plus, negative 9 plus 2 gives you negative 7. See that? Okay. Then I want, now they're not always set up this nicely, okay? You might have to work with this one and this one, or something like that. So now I'm going to combine these two, okay? So when I get x plus x gives you 2x, 4y and 2y gives you minus 2y. And again, the z's cancel out, which is very convenient. See that? And 1 and negative 9 gives you negative 8. Yes? Yes, sir.
What happens if they don't cancel out evenly? Because the book tends to do that. They give you like a perfect example, and then when you actually go to the problems, it doesn't apply to anything.
Then use matrices, or you say this one doesn't work. Because a lot of times what I try to highlight on this sheet is more often than not, these things are not going to have a solution. If you just make one up randomly, probably it's not going to have a solution. Because like if you think of 3 sheets of paper, the likelihood that they're going to cross at exactly one point is not very good, right? You know, so if you just make it, so the problems that work, they're kind of like contrived problems. You know, they have to make them work. Anyway, but with 3 lines, it would be to get 3 lines to intersect. It's not as bad, but 3 lines, you have to graph with parametric equations, and that's kind of a pain in the neck. So we're not going to go there. So anyway, then what I would probably want to do is multiply this top one by either 2 or negative, probably by 2, right? Let's multiply this top equation by 2. Good. And so if I multiply that top equation by 2, then I get negative 2x minus plus 2y equals negative 14. And then I add these two together. See what I did? Multiplied this by 2 to get this. And then I add this together, and I get 0 equals negative 22, right? And what that means, what does that mean? Either a couple of these are parallel planes, which I think this and this would be, okay? Or one of them is, or all 3 of them are parallel or something like that, but there is no solution to this. All right? But if you end up and they tell you in the book, they have a couple that come up with the equation of the line where they intersect or something like that. I'm not going to go there because it's a headache and it's kind of beyond where I really want to go. But if you did end up with something like 0 equals 0 or 5 equals 5 or something like that, that means that these things are probably intersecting all those planes are intersecting on one line. I don't know if I could draw that. Could I draw that? I'm not gonna even try. You know what I mean, right? Well, never mind. Okay, so anyway, that's enough about that. So just so you know, they can intersect in this way. And then we have all these application problems. First, I'm going to do these two. Then I'm going to teach you how to solve with matrices, and then we'll do a couple more. So this one, this is kind of a good problem because it says find real numbers a, b, and c so that the graph of the quadratic function y equals a x squared plus bx plus c passes through these 3 points. So this is kind of cool. You have these points, and you want to figure out what the equation of a parabola that goes through those 3 points is. So the way I would do that is, and I always have a test problem like this, so you should know how to do this. It's pretty easy. You just plug in this number for y and this number for and the other number for x, and you come up with 3 equations. 3 equations and 3 unknowns, which is what you need to solve the system. So for this one, I plug in -4 for y, right? In this one, and then I plug in -1 for x, and -1 squared gives you positive 1a, and then I plug in -1 for b, minus b. And then I plug in, well, there is, and plus c, because c doesn't have a
Why is
an
it
x.
okay?
Why? Because you take the -1 and you square it, right? And you get 1a. All right? Everyone see where I got equation 1 from? Using this point right here. Then I'm going to come up with an equation using this point. So that has 6 equals 1 squared times a, well, let's just call that a. I should have just called this, let's just call this a instead of 1a. Okay? And then I have 1 times x, or 1 times b, which is just plus b. And then I have plus c, because there's nothing to plug in front of the c. The third equation, I have 0 equals what? 9a. Everyone see where that came from? 3 squared. Okay. Plus 3b plus c. And now this is a relatively easy system to solve by hand, so I'm just going to do that. I'm going to subtract these 2 equations. Or I'm going to subtract this one minus this one. Is that what I'm going to do? Sure. So if I subtract 6 minus 4, I get 10. I'm subtracting upside down. B minus b, I get plus 2b. Everyone's okay? I'm subtracting this equation from this equation. This minus -b. What's c minus c? 0. So I get, whoops, 10 equals, what am I doing? 10 equals a minus a gives you nothing. I get a 2b, right? Is that what I should have gotten? 2b equals 10. So that's nice because that tells me what b is right away. B is 5. Yes? Good? And then I'm going to subtract these 2 equations. And then let's subtract the top one minus this one. You can do anything you want with these as long as you're consistent. So I'm going to take these 2 and subtract them. And that gives me 6 equals a minus 9a means -8a. And b minus 3b gives you minus 2b. And c minus c gives you 0. So I get 6 equals -8a minus 2b. And then I take b and I put it in there. And I have 6 equals -8a minus 10, which means that -8a equals 16, which means that a equals -2. Right? Did I make a mistake yet? Probably. All right. So then I want to find c, which I haven't found yet, so I could just plug in probably the easiest equation to plug in. I know that if I take this equation, and I know A and B, right, I know that 6 equals A, which is -2, plus B, which is 5, plus C. So that means that C equals 3, right? C equals 3. So now I want to find, don't just find A, B, and C. It says find real numbers A, B, and C so that the graph of the quadratic function passes through those points. So I get y equals A, -2x squared plus b plus 5x plus 3. And that, what plus 3? And that parabola would go through all three of those points.
Mr. Leader,
Yes, ma'am.
how did you figure out that you were gonna subtract the top equation from the second equation? Like, would you have gotten the same answer if you had added them?
Yeah, I could have eliminated the b's instead of the c. Yeah, any way you want to do, but the goal is to eliminate one of the variables. And I'm looking at these three equations, I said, well, I have a 1c here, a 1c here, a 1c here. So it'll be easiest to eliminate c from both of these and c from both of these, you see. I mean, I could have eliminated the b's here by adding, but then I could combine these two by multiplying this equation by 3 and then subtracting. That would have worked too, but it would have been more steps, you see. So yeah, you could do it any way you choose, but I think mine was the most easier way. Yes? A stat plot, and then go quadratic fit. Yeah, but that's really, I mean, you want to do it algebra. I want to see algebra. Yeah. All right, especially on a pretty simple one. Okay, next type of problem that you might encounter is one like this. Look, I made up another favorite problem. Lance can ride his bike 60 miles with the wind in 2 hours. That's pretty fast, isn't it? Okay. On the return trip, the same distance takes him 2.5 hours. How fast is the wind blowing? What is Lance's speed without the wind? So this is a rate times time equals distance problem. Let's choose a different color. I'm tired of this. Let's get a deep, rich green. Purple? What color? Give me a color. You don't care. What color am I painting it right now?
Black.
Black? Black is bad. Is that black? Okay, let's see. Oh, there it is. All right, so Lance can write this. So you know that this is a rate times time equals distance problem. And so what you want to do is let's do B equal Lance's speed without Lance's speed without wind, and let W equal the wind speed. And so what you know with this one, on the return trip, the same. So going, he has, his rate is B plus W, right? Because he's got the wind pushing him. You understand that? Yeah? Okay. Times, that's his rate. His time is 2 equals 60, right? And then coming back, he has the wind is pushing against him. So he has B minus W times 2.5 equals the same distance, right? He does the same distance coming back. He goes 120 miles. That's nothing for Lance. He's a man. All right. So then what you do is you divide both sides by, you could distribute and then solve the system, but I think it's easier in this case, since this is divisible by 2.5 and this is divisible by 2. It's easy just to divide both of these equations by 2. So if I do that, oops, I hate when I do that. Oh well, it's okay. So if I divide both sides by 2 over here, I get b plus w equals 30. So I divided by 2 here, I divided this by 2, which I'm allowed to do. And then I'm going to divide this by 2.5 and this by 2.5. And I get b minus w equals 24. And now I solve by elimination. Add those two together. I get 2b equals 54. And so b equals 27 miles an hour, right? And therefore the wind must be going how fast? 30, right? Because you know that b plus w equals 30 and b minus w is 24. So w must be 3. So the wind is blowing at 3 miles an hour, and he could go 27 miles an hour without the wind. Probably about right for Lance Armstrong. When I ride my bike, I average about 15 miles an hour. That's how fast those guys are. Anyone ever seen the pro? All right. So now you want to get to the good stuff. You want to know how to solve with matrices, okay? And here's a couple problems. I don't know if I'll do this one. I think I'll just set up this dietitian problem. But solving with matrices, no, matrices frequently do not have an inverse. This says if you have a system of equations right here, okay? A, B, and C represent these constants over here, okay? 8, 23, and 53, okay? A represents the matrix, which is the coefficients of these three equations in this order, right? So in this case, this matrix would be 1, negative 2, negative 1, 2, I'll do this one to kind of show you, okay? And then you take the inverse of that matrix and you multiply it times the constant matrix, and you end up with x, y, and z. How many of you done that before? You've done that before, okay? Makes your life kind of easy. Now I don't know if you care, but I wouldn't mind showing you why that works. Because why it works, if you have some matrix A, so A times, if you multiply that by its inverse, it's kind of like dividing by, or multiplying by the reciprocal. If I multiply that by that, I end up getting this thing I, which is called the identity matrix. And the identity matrix is a matrix that just has ones going this way. Anyone ever see this? And zeros in all the other spots, okay? 0, 0, 0. And the way you multiply matrices is you take this and you multiply it. So say you have 3, 2, 5 over here. You take this row, you multiply by that column. You take this row, you multiply by that column. You take this row, you multiply that by that column. And then you end up with the result, okay? What happens if you multiply this by its matrix, you end up canceling them out and getting I over here. So if I take I, and if I multiply both sides by the inverse of that, what happens is I get this over here and the answer over here. Algebraically it works out, okay? But this is called the identity matrix, which is what happens when you multiply a matrix by its inverse. And algebraically, this is the result, okay? And so now, if I want to solve this system using matrices, the way you do that is you put it in your calculator. And I hope this one works, because last night I don't think it was working. So I'm going to get out of here, close this, get to my calculator somewhere, get rid of that calculator, this, my calculator. Last thing. Let's do the last problem on it. As soon as I get my calculator. Go. Hurry. I'm going to go options, always in the front. And I'm going to go back, what is in front? I could hide this. That's better. So, can I make it smaller? Maybe. Oh, I could just grab, let's just grab this. How do I grab this problem? Let's hide this. Grab this problem. And we're going to do this one with matrices. Okay? So you will see one like this as well. So I want to show you how to do it. Where'd my calculator go? Calculator, come back. All right. I don't know. Here's my calculator. Oh! But then what? Technologies. Supposed to be on top. There we go. Okay. So this is kind of problem you might see. You will see. So a dietitian wants a patient to have 65 grams of protein, 95 grams of carbohydrate, 900 grams. There's all these numbers and stuff, okay? And it's kind of another contrived problem, but it works. So now I can't write because I don't have my workspace anymore. Oh, crap. Come on. Where'd my workspace go? What's that do? See it? I'll get there. Don't worry. Calculator. Now I need, all I need is a calculator. Calculator. There we go. Where'd my workspace go? Workspace go. Now I can write, right? Right. Oh. I give up. Should I give up? No. I'm not giving up. Okay, now where's my calculator go? How come when I do that, my calculator just... Oh well. Anyway, so let's just scroll down there. Now I lost my pen. Can I squish this over? No. Okay, I quit. There, do your homework. No, don't do your homework. Just set it up. Is you have 65 grams of protein. So over here, you put 65. This is your protein equation. Protein over here. All right, protein. And you get 65 equals, and the food service tells us dinner per day is chicken, potatoes, and 2% milk. No, each serving of chicken has 30 grams of protein. So what you have is 30 for your chicken. Okay, you have each serving of baked potatoes has 4 grams of protein. So you have 4 for your potatoes. And then each glass of milk has 9 grams of protein, plus 9. For, what is that? Milk. You guys see where that equation comes from? Okay? This is all your proteins from your 3 different food groups. And this is how much protein you're allowed to have. Then you have another equation for carbohydrates. 95 grams of carbohydrates, carbos. All right? And so it tells you that each thing of chicken has 35 grams of carbos, right? 35 grams of carbos. Each thing of baked potatoes has 33 grams of baked potatoes, 33 p of carbos for potatoes. And each glass of milk has for M. Then you set up one more equation. And you want to have 905 grams of calcium. So then, you, let's see, each thing of chicken has how much calcium? 200? 200 calcium. Each thing of potatoes has 10 milligrams of calcium, and each thing of milk has 300 grams of calcium. 300 for milk. And now I put all this stuff into my matrix, one matrix, and I put this into another matrix. Now the way you do that is by losing all this stuff, getting your calculator, going back to those equations. Where does equations go? Where does equations go? There they are. So to do this, you go to second, where's matrix? Right? Go away. Oh, come on. Going crazy. There. I'm gonna move this. Squish this. So I'm gonna go to matrix. Is that right here? Matrix. No. Clear. I was doing this last night. Matrix. Is it under math?
No,
No, it's down one.
Right here?
Yep.
Second matrix. Not gonna see them come up. Second matrix. Where? Here? Yep. Does that say matrix right there? Clear. Let me try again. There we go. Second matrix. And you go up to, you hit A. Okay? No, you don't. You go second matrix, and you go to edit. A. And you want to call that a 3 by 3 matrix. So you go 3 by 3 by 3. And then you hit enter, and then you'll get 3 rows and 3 columns. And then you put in these numbers, okay? 30, enter, not 4, enter, 9, enter. And you can just keep going, 35, enter, 33, enter, 13, 200, 10, and 300, right? And then you go to matrix B. So you go second quit, second matrix B, and you want to edit that one. And you want to make that one a 3 by 1, okay? So first I want to go to edit, then I want to go to matrix, then I want to hit enter, and I want to make that a 3 by 1. Okay, and then I'll have these down here, and I want to put in the numbers 65, 95, and 905. And then, once I have matrix A and matrix B in there, I go second quit, and clear, whatever, clear. And I want to go the inverse of matrix A times matrix B. So I'm going to go second matrix A, but then I get the inverse over here. X to the negative 1, that takes the inverse. That's a matrix that if I multiplied A by that, I'd get the identity matrix. Times second matrix B chicken, 0.5 servings of potatoes, and 2 servings of what, milk, okay?